So we're going to draw the NMOS input with a PMOS active load version that we've been looking at. Alright, our input transistors are our NMOS transistors M1 and M2. They're loaded by our active PMOS load M3 and M4. And finally, we have a tail current source M5 that's connected to a DC bias generator. So here's our input, VI1, and our other input, VI2, and of course we take our output from between transistor M2 and M4. Now oftentimes we're going to connect this to another circuit, and that other circuit might have some capacitance that we'll call CL, or load capacitance. And we also have the internal capacitance from the device. So we would have a CGD for M4, we would have a CDB for M2, we would have a CGD for M2, and we would have a CDB for M4. Now we've already found the total resistance at this load, and so we'll just remind you of that. Remember, big GM for this circuit was equal to little gm 1, 2, and our total for this circuit was equal to RO4 in parallel with RO2. So in order to find the open circuit time constant at this node, we would just sum all of the capacitors. They would all add in parallel, and we would find that CL prime, which we'll call the total load capacitance, would be equal to CL, whatever the capacitance is of the circuit that we hook the device up to, plus CGD 2 plus CGD 4 plus CDB 2 plus CDB 4. Now, making the dominant pole assumption, we would just say that our high frequency pole, F of H, is equal to 1 divided by 2 pi times RO2 in parallel with RO4 times CL prime, this total capacitance term that we just found. Now there's one major problem with this type of circuit, and that's that we might like to design an operational amplifier to work over many different types of circuits that we might connect it to. In other words, we might want our operational amplifier to be general purpose. And the problem that we have with this circuit is that the bandwidth is going to vary depending upon the type of circuit that we hook our operational amplifier up to. So if we hook it up to a large capacitance, it's going to have a smaller bandwidth, and if we hook it up to a small capacitance, it'll have a much larger bandwidth. We don't want the pole frequency to vary with the type of load that we connect our op amp up to. And the reasons for this are that it affects the bandwidth. That's the obvious one that we just looked at. But as we'll start to look at, it also can affect the stability of the op amp. Now this isn't much of a problem for a single stage op amp such as the one we're looking at, but remember we said that this is not a good op amp right now because it has a high output resistance and it doesn't quite have high enough gain to be useful as an op amp. So we're going to have bandwidth issues and stability issues if we use this configuration. So let's remember the characteristic of an ideal op amp is that we have infinite gain and infinite bandwidth. So in the next part of the lecture, we're going to look at what happens if we have finite gain and finite bandwidth.